Welcome to my presentation on energy harvesting techniques for unmanned aerial vehicles used in long-endurance military applications. My name is Tepo Dibedi Mabutu, and I'll be providing this presentation as part of HMELE 80 module in the Department of Electrical and Smart Systems at UNISA. Unmanned aerial vehicles, or UAVs, have become a central part of modern warfare and military operation. They fulfill a crucial role in intelligence, surveillance, and reconnaissance. The latest UAV carries sophisticated sensors, such as your synthetic aperture radars, which dramatically increase their operational capability. However, they present with a significant challenge of power consumption. Expeditionary military UAV missions require UAVs to carry such payloads and requires a reliable and sustainable power to supply and maintain the effectiveness of these UAVs over a large remote area. Traditionally, long-endurance UAV rely on internal combustion engines because of their high energy density. However, these engines face challenges such as depleting fossil fuel as well as high environmental impact. With that said, they are still the most suitable solution for long-endurance operations. Batteries can be taken as an alternative, however, they are not viable due to their low energy density and charging time. Hence, we have to look at alternative energy sources, which must be explored to extend the operational endurance and support the demanding energy demands of these UAVs. Now for the problem statement. The integration of active SAR sensors with medium altitude long endurance UAVs presents a critical challenge due to the high power consumption of the sensors. The size and type of sensors on UAVs can limit the flight endurance and operational effectiveness of the said UAV, which is critical in military ISR missions in regions like Africa, where extensive surveillance over large and remote areas is required. The reliance on UAV batteries to meet the power requirements reduces the endurance of the UAV. To address this challenge, there is a need to develop and optimize an energy harvesting system that will supplement the power system of the UAV during flight. Now we take a look at the objectives. The main aim of this research project is to investigate and model a hybrid energy harvesting system that supports an existing UAV power system. The project objectives are as follows. 1. Investigate available hybrid energy harvesting techniques for made UAVs. 2. Design a power system combining solar energy harvesting with conventional fuel-based power. 3. Implement advanced power management to dynamically allocate harvested energy between the payloads and the UAV, as well as the UAV batteries. 4. Model and simulate this hybrid approach within a relevant mission environment. For the user requirement, the following specifications should be observed at the completion of the research project. The hybrid system should produce additional power output compared to the baseline power produced by an identified male UAV system. The system should be able to distribute the additional power to the payload or sensor as well as to the UAV battery through a power management system. The hybrid harvesting system should be able to achieve at least 1.5 energy conversion as compared to the baseline power for the solar harvesting component under peak sun conditions. For delimitation, this project is limited to the power system aspects of the male UAV, which may be utilized for long endurance applications. Although the research will investigate various energy harvesting techniques that can be used in UAVs, the simulation and theoretical modeling will be limited to the solar energy harvesting system and its integration into existing power infrastructure of the UAV. On the theoretical background, we looked at the different energy harvesting techniques. First, we started with solar energy harvesting technique. This technique has two ways in which energy can be harvested. This can be done through solar to electrical energy, or it can be done through solar to thermal energy harvesting. For UAV applications or for integration into UAV application, we'd have to look at electrical energy that is harvested through solar. This is done through photovoltaic materials that can be integrated into the infrastructure of the UAV, and thus that energy can be harvested through that technique. The second option we looked at is piezoelectrical energy. This is electrical energy which is harvested by changing mechanical energy to electrical energy. So basically, the electrical vibrations of the aircraft can be harvested to produce electrical energy. This type of piezoelectric energy harvesting is called the direct piezoelectric effect, where mechanical energy is converted into electrical energy. The next option we looked at is wind energy harvesting. This technique can be applied through two things. It can be done through wind turbine, or we can also apply the piezoelectric effect and harvest the energy from mechanical to electrical energy by harvesting the energy that arises from the effect of the wind on the aircraft. The next energy harvesting technique we looked at is radio frequency energy harvesting. This is done through harvesting energy from RF sources. This can be ambient RF sources or it can be dedicated RF sources. An example of the RF sources can be your Wi-Fi, your LAN, or your Bluetooth sources. Energy is harvested from these systems using their radio antenna as well as other electrical circuits in order to convert that RF sources energy into electrical energy. The next thing we looked at during the theoretical background is the power management system. The power management system can consist of the bus systems, the redundant pathways, dynamic configuration, and prioritization. The bus system is where primary and secondary buses are used in the system. The primary buses will contain essential system or critical system, and the secondary buses will power the non-essential systems. The systems also employ redundant pathways in order to allow that if power is lost in any of the buses, then the secondary or the next bus will be able to provide power to the systems, especially the essential or critical systems. Then the system also have dynamic configuration. This is where if the system has low power or is experiencing low energy, then prioritization can be done to ensure that essential systems are powered during the mission or during the flight until the aircraft has safely landed. For the conceptual design, after investigating multiple or various energy harvesting techniques, the solar energy harvesting technique has been chosen as a system that will be integrated, or the technique that will be integrated into the power density or the power system of the UAV. For implementation, the project will utilize solar harvesting to improve the UAV's power density. The system configuration simulates fuel-based propulsion, solar harvesting, power management for propulsion and avionics, and the primary requirement is to sustain flight with minimum battery sizing, focus on reliability, and improved endurance under varying sunlight conditions. Continuing with the conceptual design. The system configuration will be the double shaft parallel configuration, which will be utilized to simulate the hybrid propulsion system for the UAV. This configuration consists of the fuel, which will be avgas, and the internal combustion engine. Then we also have the transmission system and the PV cells or the photovoltaic cells, the battery storage, as well as the electric motor. All of this will be used to propel or to power the propeller for thrust for the aircraft. In order to simulate the hybrid UAV power system, integrating the energy harvesting techniques, we have to model the different subsystems that go into the system. First, we'll start with the internal combustion engine subsystem. For this project, the Rotex 915 aviation piston engine will be considered. The power obtained from this engine can be calculated using the different technical data that has been provided on the side. First, we will be calculating the power output that this engine can give us. This is done through this formula attached here, where power is equals to the efficiency of the internal combustion engine multiplied by the fuel mass flow rate multiplied by the lower heating value of the fuel. Thereafter, we can calculate the thermal efficiency of the ice, which is given by mechanical power output divided by the fuel energy input. In order to model the fuel consumption, we use the following formula. The fuel flow is equals to the BHP times 3,600 divided by the BSFC times 1,000. The BHP refers to the brake horsepower and the BSFC refers to the brake specific fuel consumption. For the Rotex 915 engine, it typically consumes between 28 and 32 liters per an hour. This is at cruise with fuel density of approximately 0.72 to 0.76 kg per liter. This is when we are utilizing the avgas. So the fuel mass flow rate is therefore given by 30 liters multiplied by 0.74 kg per liter divided by 3,600. For the specific UAV or the system that we will be utilizing, then we'll be using the fuel mass flow as 0.00617 kgs per second. For the solar subsystem, the following has been considered. For the simulation, a high-efficiency PV cells will be utilized. Gallium arsenide cells, which are multi-junction PV cells, have an efficiency of about 30 to 40%, making them the most preferable solution to optimize the solar energy harvesting. The technical data for these PV cells is on the right, as shown in the table on the right. In order to calculate the power output of the solar cells, then we take the irradiance multiplied by the effective area that the solar cells will be covering and multiplied it by the efficiency of the solar cells, which we will take as 35%, just in the middle between 30 and 45%. To simulate the battery storage subsystem, the following will be considered. The battery will be supplied power and charged by the internal combustion engine as well as the solar energy harvested. The energy storage is governed by the following. It is equals to the power from the MPPT plus the power from the internal combustion engine minus the power to the motor minus the power to the avionics and minus the power losses. For simulation purposes, a 60 ampere hour a lithium-ion battery with an MPPT charge controller will be used for simulations. For the electric motor subsystem, the following has been considered. A brushless DC motor will be utilized due to their high efficiency and good power to weight ratio. This motor will be supplied with power, and this power is given by voltage multiplied by the current. The torque and speed relationship is defined by the mechanical power or defines the mechanical power and is given by the following formula. Power is equals to torque multiplied by the angular velocity. In order to model the propeller subsystem, the following has been considered. To power the propeller, the total power input will come from the internal combustion engine as well as the electric motor, which is supplied by the battery. This will go through the transmission to the propeller. This combined power turns the propeller and generates thrust, and it is given by P propeller is equals to power output from the internal combustion engine plus the power from the motor. Besides the propulsion system of the UAV, the biggest consumer of power on the system would be the avionics, especially when they include the sound sensor. This is primarily supplied from the battery, which is powered by the solar energy harvested. The load from the avionics, including the sound sensor, is given by P avionics is equals to power that goes to the sound sensor plus power to the avionics. The next subsystem that will be modeled is the power management subsystem. The objective of the power management system is to prioritize the continuous power delivery to the avionics and sound sensors, as well as to maintain the mission capability. The power system must also efficiently split propulsion power demand between the eyes and electric motor to optimize the fuel use and the solar energy harvested. To sufficiently to supply this power demands, the battery state of charge must stay within the following constraint, this as indicated in the formula below. To power the propeller, the combined power from the internal combustion engine and electric motor must meet or exceed the power needed to maintain the desired flight conditions. These conditions can be shown as following. So, power from the internal combustion engine plus the power from the motor will be equal or greater than the power to the propeller or the propeller demand. The power management will control the operations to prioritize critical systems of the UAV during flight to optimize the fuel and electrical energy use. For the simulation of the system, the following were considered. To simulate the hybrid power system for a manned UAV, virtual models were constructed using MATLAB and Simulink. In Simulink, a model was created with the solar PV subsystem, the I subsystem, battery subsystem, motor subsystem, power management subsystem, the CVT subsystem, and finally the propeller subsystem. All of the subsystems were combined in order to create one hybrid power system for the UAV. The subsystem started with the ICE or internal combustion subsystems connected here, and then the solar PV subsystem with the effective area and solar irradiance is going in as an input. Then the output of that goes to the battery subsystem, which further goes to the motor subsystem. Right. The power management subsystem also comes out from here, which comes in from the internal combustion engine and goes to the motor, and also it goes through the transmission. Then the transmission subsystem then goes to the propeller of the system. So this entire subsystem makes up the hybrid power system for the UAV. Now, the solar subsystem was simulated using the irradiance profile as well as the effective surface area and the efficient conversion of the PV cells that were used. The irradiance profile takes into consideration that the irradiance intensity changes throughout the day, with the highest intensity experienced during midday. The effective surface area was taken from a typical male UAV, which, for instance, you've got the Melco, which during the development, the surface area could be approximately about 12.5 meters squared, and the Seeker 400 from Diral Dynamics, that one has a wingspan of about 10 meters, and combined with the part of the fuselage, the surface area is approximately about 12.5 meters squared. Then we took the conversion efficiency of the gallium arsenide PV cells, which was between 30 and 40%, and we stuck with the 35% in order to simulate the system. All of these considerations are taken, and in order to be able to give a more realistic power output for the solar. So the I subsystem was simulated as a functional block in Simulink, representing how energy within the engine flows from the fuel to the mechanical power output. The simulation accounted for the fuel properties, engine efficiency, and also operational conditions. So if we can look at the Y1D lookup table block here, this block was used in order to be able to put in the input of the engine condition, operational conditions of the engine at a time, looking from when the engine starts up until it starts climbing, until it also starts to be on a cruise. So this is to try and simulate the operational conditions that the engine will be operating in. Now, for the battery subsystem, the system was simulated to model real-time charge and discharge of the battery from the solar model and the ICE model. The total power going into the battery was calculated by summing the incoming power from the solar and the ICE generator, which will be a generator that is run from the internal combustion engine, and subtracting the total load. The subsystem further considers the battery state of charge to ensure the management of the balance between the source and the demand. The motor subsystem models the conversion of the stored battery energy into the mechanical power output of the motor. This power is then utilized to run the propeller of the UAV. The model accounts for both the electrical properties of the battery and the efficiency of the motor. So the box here, the input ports here, takes into consideration all the battery characteristics, and that those characteristics then are put into considering the motor efficiency, then all of this then gives us the output or mechanical power from the motor. So the power management subsystem models the real-time allocation and prioritization of available energy between the UAV propulsion and avionics load. The subsystem does this while enforcing system constraints such as the minimum battery state of charge and power threshold. The subsystem ensures that critical loads such as the propulsion always have priority, and non-essential loads can be shared if the overall system energy is low. So the subsystem or the simulation takes the switch blocks within Simulink in order to create conditions in which way, if power is low or energy is low, the system then can switch accordingly. For instance, if the battery state of charge is low, the system will completely switch to the internal combustion engine power. So this ensures that load is prioritized, and also it ensures that a load is shared if a system is experiencing low energy conditions. The propeller subsystem was utilized to model the conversion of mechanical power from the hybrid power system into useful thrust while taking into account the efficiency of the propeller itself. This approach utilized a simple but realistic approach to analyzing the model for hybrid propulsion system. So the power that is coming out from the transmission will go through the shaft, will go through the prop efficiency or the gain, where we consider the efficiency of the propeller, and this power will be turned into thrust in order to give the aircraft lift. This power is simulated to show that the aircraft or a combination of the two sources of energy, the ice and also the solar energy harvester, will be able to power the system. Yeah. Next, we'll look at the results and the discussions thereof. First, we'll be considering the hybrid system power output. So for the hybrid system power output, we'll look at first the output plot for the internal combustion engine as shown on the right. The ICE power output plot shows that the power output of the ICE reaches and maintains a value of well above 80 kilowatts, which is around here. So the plot shows a dynamic response and sustained capability of the fuel-based system. So the plot shows that the system starts off considering the operational conditions of the aircraft, where we start off with when we're starting off the engine or turning on the engine, which has a very significant climb or significant amount of energy that is being pulled. And once the engine starts climbing, it still consumes a large amount of power for a shorter period. And once the engine has achieved the climb, it also becomes stable within that. So the flat sustained movement of the plot indicates that the engine can provide a strong sustained baseline power for the hybrid system. Yeah. So continuing with the hybrid system power output, we will look at the solar plot output. So for the solar plot output, as shown on the right here, it shows that it shows a typical curve for solar energy harvesting, where the power output rises after sunrise or during low irradiance profiles, and as the profile increases and goes towards its peak, then this is where it will peak around midday, and it will be able to provide nearly 4 kilowatts on its own until that profile then will initially just go down. This contribution forms part of the solar harvester, and it shows that a substantial amount of power can be gained from the solar energy harvesting. So the two plots that were given from MATLAB shows the main benefit of a hybrid system. The ICE ensures that there is a baseline reliability within the power system by supporting steady power whenever needed to allow for night operations of the UAV or operations under cloudy conditions. The solar harvester, however, also provides significant supplementary power to the system for daylight operations of the UAV. This will result in a decrease in fuel use, enhancing the endurance and increasing the sustainability of the UAV. During peak sun conditions, the hybrid system can shift the bulk of the power supply from fuel to solar and battery charging, which allows for the storage of power for later use. While the conversion efficiency is about with the conversion of efficiency of about 30% from the PV cells. The solar harvester system can contribute to approximately 5% of the internal combustion engine power, which, while modest, can reduce the fuel use and power avionics and charge batteries in hybrid system. Now we take a look at the power management system's results and discussions. The power management system ensures that there is clear routing of ICE and solar power harvested. The power management system ensures that the energy is dynamically allocated with propulsion as the main priority for the harvested power, ensuring less fuel is used when we are at peak sun conditions. This ensures that the UAV endurance can be extended while still avionics, including a SAR sensor, can be supported throughout the flight. Based on the result of the simulation, it can be determined that integrating a harvesting system, especially one with a high power yield such as solar, will increase the overall power produced by the conventional UAV system, increasing endurance and efficiency of the UAV used in military operations. At this point of the presentation, we'll look at the challenges encountered throughout the process of this research project. The first challenge that I encountered was that there is limited research on male UAVs. Most research available on UAVs covers the smaller UAVs that do not have the same power requirement as male UAVs. These UAVs do not suffer the same challenges that male UAVs have. In order to be able to mitigate this risk or this challenge, what I did is I had to look at smaller aircraft or smaller manned aircraft in order to be able to try and map out what the architecture of male UAVs will look like. And information on male UAVs is information that is mostly proprietary and will likely be classified. So the limited research that is online was used to try and put together what the power system or architecture of these UAVs will look like. The next challenge that was faced was finances. Most of the research that is available and latest research that is available is quite expensive to get. There's books that were going at the ranges of 500 US dollars, which is quite a lot of money and would have actually gone beyond the budget that I had placed. In order to be able to mitigate this challenge, I had to look at alternative sources, free research papers, and try to put together sound research, especially for the literature review. Next, we look at the budget of the project. The table below represents the approximate cost of the research project. Some of the cost was reduced by utilizing trial software through the UNISA student email, and the reduction of travel costs by utilizing online resources for the research. So instead of using a paid software, I used a UNISA email to try and get myself a trial for MATLAB and Simulink. Also, in terms of travel cost, all my research was done at home using the internet access, which has been accounted for through the data in order to do my research. So only online resources were utilized during this research. This reduced the cost of my research and brought it down to about 8,608 rands. Next, we look at the project timeline. The envisioned time from planning to execution of the research project was 7 months. The structured schedule ensured that research progress was tracked by ensuring that there are deliverables to be met throughout the project. Initially, it started with the literature review, then the project proposal, system design, system modeling and simulation, data analysis, and report writing, which began from the 15th of September and to be concluded by the 3rd of October on the submission date. In conclusion, in this project, we demonstrated that the modeling, simulation, and evaluation of hybrid UAV power system by integrating a solar harvesting technique into a typical fuel-based power system. This was done by evaluating the different energy harvesting techniques that can be applied to airborne systems. The critical analysis of these techniques showed that solar energy harvesting has the most potential for applications on male UAV platforms as the technique has the highest power yield. The solar harvester, together with battery storage, can be successfully integrated into a propulsion system using a double shaft parallel configuration. The results show that ICE provides essential continuous baseline power for propulsion, and the solar harvester contributes approximately 5% additional energy under the sun peak conditions. Although modest, this contribution ensures fuel savings and enhances the endurance of the UAV. The robust power management ensures that essential systems are prioritized and ensures the availability of power during various operational scenarios. Overall, the research project highlights how hybrid power system can extend UAV operations through increased power availability. This concludes my presentation, and thank you very much for taking your time to listen to it.